So this is a calculus lecture for Friday, March 20th. It's absolute and conditional convergence. That's the first part of section 9.6 in your Stewart-Kokoska. There's a couple more parts to it, but we're going to start with this. So what this starts with is some things that we know. We know that the sum from n equals 1 to infinity of 1 over n diverges. All right, diverges because it's a p-series with p equals 1, but we can also say that it is the harmonic series. We can say either one of those things, harmonic series. And I like harmonic series because it's sort of poetic. Then we can observe the sum from n equals 1 to infinity of negative 1 to the nth power, or sometimes we put n minus 1, depending on whether we want the first term to be positive or negative. Negative 1 to the n power of 1 over n. Now, this series we showed last time converges by the alternating series test. Converges by the alternating series test, which says that if I have an alternating series, the negative 1 goes alternately positive and negative. So, so these terms, like if you compare them, this first one is going 1 plus 1 half plus 1 third plus 1 fourth plus 1 sixth. This one is starting at negative, so it's negative 1 plus 1 half minus 1 third plus 1 fourth minus 1 fifth, etc. So this one's alternating. And that one we showed last time, because we can use the alternating series test, just says that if I ignore the alternating part, look at the positive part, we usually call it b sub n, and if that b sub n is both decreasing and positive, and also has the limit 0 as n approaches infinity, so the limit as n approaches infinity of 1 over n is in fact 0, that means that that series has to converge by the alternating series test. So converges by the alternating series test, and we say that, we call that, by the way, the alternating harmonic series. Alternating harmonic series. So the harmonic series diverges, but the alternating harmonic series converges. So that's an example of a series where the sum of the alternating series converges, but if I take just the positive values, it doesn't. So what we say about the sum from n equals 1 to infinity of negative 1 to the n times 1 over n is that it converges conditionally. So converging conditionally means that the sum of the series converges, but if I take the sum of the absolute values of the series, it does not converge, diverges. So that's called converging conditionally. All right, so if I say the sum converges, I'm just talking about the sum as it is. If I ask about conditional or absolute convergence, then I'm asking what happens if I take the absolute value. And of course, that only makes sense to do if I had an alternating series or some other series where some of the terms are negative, because if a sub n is positive, then sum of a sub n and sum of absolute value of a sub n are the same thing. And then there's sort of no question as to what they're doing. So let's compare this to another series. So we know that the sum from n equals 1 to infinity of 1 over n squared converges, because that's a p-series with p equals 2. So that's a p-series. P equals 2, nothing magic about the number 2. It could be 1.5, it could be 60 billion. As long as it's greater than 1, this series converges. All right, but what about sum from n equals 1 to infinity of negative 1 to the n of 1 over n squared? So here I'm adding up 1 plus 1 fourth plus 1 ninth plus 1 16th plus 1 25th, etc. Here I'm starting with a negative value and I'm doing negative 1 plus 1 fourth minus 1 ninth plus 1 16th, etc. So it sort of would make sense that since I'm just adding the same terms, but some of them were negative, that if this one converges, then this one's going to converge, and that turns out to be true. We can also conclude that this converges, the alternating version converges because by an alternating series test. So we could sort of write that out explicitly, because I think we need a little work on justifying some of these things explicitly. So what we're going to observe about this is that 1 over n squared is positive and decreasing, and limit as n approaches infinity of 1 over n squared equals 0. So sum n equals 1 to infinity of negative 1 to the n of 1 over n squared converges. And if I want to justify this, I have to say by the alternating series test, by alternating series test. So that's one way that I know that converges. So another way that I know that this series converges is that if I think about the sum from n equals 1 to infinity of the absolute value of this sequence, negative 1 to the n times 1 over n squared, well, that's equal to the sum of n equals 1 to infinity of 1 over n squared, which we know converges. I won't write the reason this time. And there's a theorem in your book that says that if the sum from n equals 1 to infinity of the absolute value of a sub n converges, then the sum from n equals 1 to infinity of a sub n converges. One way to think of this is that absolute convergence, if the absolute value converges, is sort of a stronger condition than just convergence. If I have the absolute values converging, then I have to have the smaller terms, the positive terms converging. So what we call this, when in this case where not only does the series converge by alternating series test, but also the absolute value of the series converges because it's a p-series, we say that this particular sum converges absolutely. So in this case, we say sum equals 1, n equals 1 to infinity of negative 1 to the n of 1 over n squared converges absolutely. All right, so the sum converges, and it converges absolutely because the absolute value also converges. So that's, if you compare that to the harmonic series, the alternating harmonic series converges, but the absolute value of the alternating series, which is the harmonic series, diverges. So we say that the harmonic series converges conditionally. That's another nice little poetic thing you can say. The harmonic series converges conditionally. But the sum negative 1 to the n of 1 over n squared converges absolutely. That means not only does this alternating series converge, but so does its absolute value. And then you have this theorem, which we can say that, like one way to say that is that a series that converges absolutely converges. So if sum a sub n converges absolutely, implies that sum a sub n converges. All right, that's just another way of saying this same thing. These are saying the same thing. And that theorem is, it's pretty easy to sort of common sense out, but if you want to look at a rigorous proof, it's on page 700 of your book. It's not too difficult to follow. Okay, so we're going to look at one example of using absolute convergence to establish convergence, and then we're going to go into the next section of this in the next video. So the sum that we're going to look at now is the sum from n equals 1 to infinity of cosine n over n squared. So let's consider the tests that we have available for this. Can we use the integral test? Well, this sequence might be decreasing, but since cosine n is going to be jumping up and down, I'm not confident that this sequence is always going to be decreasing. It might be, and I could do a derivative and try to find that out. But even if I did establish that this sequence was decreasing so that I could use the integral test, I don't want to have to do the integral of 1 over n squared cosine n because that's difficult to do. All right? Can I use comparison tests? We've learned the comparison tests. Comparison tests require that the terms of the sequence be positive. Right? But cosine n sometimes is negative. We're doing cosine of 2, that's more than pi over 2. It's in the second quadrant, so the cosine is going to be negative, and the n squared is going to be positive. So some of the terms are negative, so I can't use comparison tests. And I can't use alternating series test either. It's tempting to use alternating series test, but this is not really an alternating series test. Now, the terms are not just going positive and negative. Because of this cosine n term, you know, if you think of the graph of cosine looking like this, and you're just going to pick whole number values of cosine, you know, they're just going to be jumping back and forth around 0, but they don't do that nice alternating positive and negative the way we need an alternating series test to do. Also, the absolute value of the terms doesn't really just necessarily decrease, again, because of this jumping up and down that happens with the cosine function. So we need something else. So what we can do is say, all right, I can't use comparison test on this sequence as it is, but what I can do is use comparison test. So I'm going to use a comparison test on the absolute value of this series, sum from n equals 1 to infinity of the absolute value of cosine n over n squared. The reason that the absolute value benefits me is that now that the terms are positive, I can use comparison test. Remember, you can't use comparison test if some of the terms are negative. So now all the terms are positive. I can even say, what could I compare this to? Well, it's pretty tempting to compare to n squared, especially since I know that cosine of n is always between -1 and 1. So I can compare. I'm going to compare to my sum b sub n is going to be the sum from n equals 1 to infinity of 1 over n squared, because that's what this sort of looks like. All right. So now what I have to observe is that my a sub n terms, so remember when you're using the comparison test, a sub n is your problem, and b sub n is your known series, a series of known convergence or divergence. We know this one converges because it's a p series. So our a sub n is absolute value of cosine n over n squared. And then since n squared is always positive, this is the same as the absolute value of cosine n over just n squared. Now, cosine n is always less than or equal to, the absolute value of cosine n is always less than or equal to 1. So cosine goes between -1 and 1. Absolute value of cosine is going to go between 0 and 1. So this term up here, this is always less than or equal to 1 over n squared. And that happens to be my b sub n. So I get what I really want to use the comparison test, which is the easier of the two comparison tests. We have comparison test, limit comparison test. As long as my problem series is less than a convergent series, I can use the simpler comparison test. So now I've laid out here an inequality, and now I can say sum from n equals 1 to infinity of, so I need to establish that the comparison series converges. 1 over n squared converges because it is a p series, p equals 2, and I've established this inequality, so sum from n equals 1 to infinity of absolute value of cosine n over n squared converges, and I want to cite the test that I'm using by comparison test. So, pay attention to how these justifications are laid out. I'm going to do a little bit more on that later. So we have, what do we need for comparison test? We need that the terms are positive. So all these terms are positive. All of these terms are positive. We need that I need to establish an inequality that my problem series is less than my comparison series. I need to establish that my comparison series converges or diverges if I'm doing that, and give a reason why it converges, and then I need to cite the test that I'm using. Those are all the parts of the justification that I need to have in there. All right, now, but I still haven't answered the original question, which was, does this series converge? So now I can say sum n equals 1 to infinity of cosine n over n squared converges because sum from n equals 1 to infinity of absolute value of cosine n over n squared converges, right? So that's just saying that if a series converges absolutely, then that series converges. So I can make a note that sum of absolute value of a sub n converges implies sum of a sub n converges, or sometimes we say the series converges absolutely, and therefore the series converges. I don't usually justify this because that's not a test or a theorem that has a recognized name. It's just something that we know. So, and again, if you want to prove that, have a look at page 700 in your textbook. Good idea, as I've mentioned before, read section 9.6. All right, so we haven't got to problems and applications yet. We've got another little section for this. So you should just go on to the next video.